Hello to everyone. So it's AMC problems. All three problems we consider today are taken from AMC-10. And I chose a specific topic. It is patterns in sequences. So in all these problems, we just have to believe in the existence of a pattern. That's it. So it's the shortest theory I've ever gave to anybody. So what is the units digit of 13 to the power of 2003? So of course you may be scared by such a big power of 2003. But let's first note something about the digit 1. So it's not the last digit of the base. So I can ignore it because I'm asked about the units digit. And the only digit that affects the last digit of the result is the 3. Of course, the power itself also affects, but this 1 definitely doesn't affect. So we can give an example, very short and very simple. Let's take 13. It ends with 3. Let's take 213. Let's take 1213. And let's power these numbers. Let's take a power of 2. It's just an example. So, of course, this number ends with 9. This number, it's a bit longer, but it also ends with 9. This number, way longer, but also ends with 9 because 3 squared is 9. So I hope I justified my idea. So the digit of 1 doesn't matter. We ignore it. So number 2. So now we consider 3 to the power of 2003. So I believe in the existence of a pattern. So in order to demonstrate this pattern, I usually use a table like this. So let the first row in the table is n. It's power of 3, and the second row is last digit of 3 to the power of n. So if n equals 1 to, I will consider the consecutive numbers for powers of n. 1, 2, 3, 4, 5, 6, 7. So we do not usually need such a long row of numbers, but it's a video where I teach you. So it's good. 8 numbers is good. So 3 to the power of 1 is 3. 3 to the power of 2 is 9. Next, what I do, I multiply the last digit of the previous power by 3, and I write the last digit only. So 9 times 3 is 27, but I write 7 only because I'm focused on last digits only. So because every time I increase the power, the index of power by 1, I multiply by 3. So I multiply the last digit of the previous power by 3. So 7 times 3 is 21, but I write 1 only. 1 times 3 is 3. Oh my God, 3. It repeats again, so it's the start of a new period. So 3 times 3, 9, 7, 1. Look, this is what I'm interested in, a pattern. It's a period or cycle. You can call it differently. So I usually call it period. So 3, 9, 7, 1. So it repeats again and again. So 4 elements. There are 4 elements in a period. So now I'm interested in order numbers of the sequence that are divisible by 4. Look, the 4th number is 1. The 8th number is also 1. So this is a pattern I'm looking for. So any order number divisible by 4 is 1. So 4, 8, 12 element in this sequence, 400 element in this sequence, they're all ones. Yep, I'm pretty sure in this fact. So now we return to the question. I need in the term 2003. So the closest number, which is a multiple of 4, is 2004. Let's write it here. 2004 is divisible by 4, so it's also 1. But 2003, which I'm interested in, is the previous term. Here it is 2003. It is 7. It is 7. So the answer is C. That's it. So it's a classical problem, and I urge you to make a study of the periodicity in the last digits of other bases. Do not consider just 3. What is the period in last digits of 2 to the power of n? 5 to the power of n, 8 to the power of n. Some of the periods are so short, because look at 5 to the power of n. It doesn't matter what power you consider, it always ends with 5. So the period is just it consists of one element, and it will be your individual investigation. So it will be so useful for you. Okay, that's the question number 1. So let's move on. The question number 2. The first term of a sequence is 2005. Okay. Each succeeding term is the sum of the cubes of the digits of the previous term. Oh my God, it sounds weird because we are so used to arithmetic sequence, geometrical sequence. What else? I don't know. Fibonacci sequence, where the next term is the sum of the previous 2 terms. But this is a bit unusual. But I believe in patterns. Every time I start solving the problems like that, I will repeat the same phrase: I believe in patterns. What is the 2005th term of the sequence? Oh my God, 2005. Again, it's a big number. They want to make me make me scared. Okay, I have to write down some first terms and catch the pattern. So 2005. Okay, it's the first term. The next term is the sum of the cubes of the digits. Okay, 2 cubed, 0 cubed, 0 cubed, and 5 cubed. So I'm good at arithmetics. This is 125. This is 8. It's 133. That's the next term. Next term is 1 cubed plus 3 cubed plus 3 cubed. I take the previous term and sum up the cubes of the digits. So 27, and one more is 55. Next term is 55. Okay, so my expectations are high because I'm waiting for a repetition. So 5 cubed plus 5 cubed is 125, which totals in 250. 250. Yeah, it's a different number, but look, it consists of the same digits as 2005. Yeah, I think we got it. So because next term is 2 cubed, 5 cubed, and 0 cubed, it's the same. It's the same as 133. So followed by 55, 250, again and again. So 2005, the first term, can be easily replaced by 250, yeah, because it consists of the same digits. So now let's group the numbers by 3. So 250, 133, 55, and then it repeats. again and again indefinitely. So, okay, I can do the same thing as we did in the previous problem. I can put the order numbers 1, 2, 3, 4, 5, 6, 7. Especially if you're a novice, it would explain a lot. So, do you remember I noticed the length of the period? It's three. There are 3 elements in the period. And then I focused on the order numbers, or the terms, the order numbers of which are divisible by 3. So they're all 55. Look, the third term in the sequence, the 6th term, 9th term, 30th term is also 55. That's the pattern we are talking about. We always say, catch the pattern, catch the pattern. Here it is. So now I'm looking for the number closest to 2005, which is divisible by 3. So we have to recall the divisibility rule by 3. So the sum of the digits must be divisible by 3. Of course, I understand it must be 2004. Right? So the sum of the digits is 6. So the number itself, 2004, is divisible by 3 because it's sum of the digits is divisible by 3. So I know this number, as all other numbers, multiples of 3, is 55. But I need in next number, 2005. Next number, as you can see in this row of numbers, is 250. That's it. So it's similar to what we did in the previous question, with just slight changes. Okay, so let's move to the next problem, number 3. Let A1, A2, and so on be a sequence for which the first term is equal to 2, the second term is equal to 3, and then starting from the third term, each term is equal to the ratio of the 2 previous terms. So it's as for me, it's important to pronounce the rule in words. This is the previous term, and this is the term before the previous. So I have to consider their ratio. Yep, I divide the previous term by the term before the previous. So they again ask about the 2006 term. So, but now we know it's just an intimidation. It's just an intimidation. We are not going to buy it. And let's write down a sequence of first terms 2, 3. Next, I do not appeal to this formula. I'm just pronouncing. The next term is the ratio of the 2 previous terms, 3 over 2. Okay, it's a fraction. Do not use any decimals. Next term is 3 over 2 divided by 3. I hope you're good at fractions. It's 1 over 2. 1 over 2 divided by 3 over 2. It's 1/3. 1/3 divided by a half. So I have to flip the fraction I'm dividing by. So it's 2/3. 2/3 divided by 1/3. It's 2. Oh my God. It repeats. So 2 divided by 2/3. Please, 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 please. Yes, it's 3. It's 3. So everything repeats again. Yep. So I usually, for teaching purposes only, I write down the 2 periods. 2 periods. Yeah, 2 full periods. Of course, I know the term after 2/3 is 2, and so on. So again, I determine the number of elements in the period, the first period. It's 6 elements. And let's write down the order numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and so on. So I'm interested in order numbers which are multiples of 6. That is, I'm interested in 6th term, 12th term. They're all 2/3. That's nice pattern. And then let's take a look at 2006. Maybe it sounds too difficult to find a number closest to 2006, which is a multiple of 6. That's why I can use long division. 2006 divided by 6. Okay, 3 times 6 is 18. 2 is a remainder. 0 goes down. Okay, 3 again. 18, 2, 6. And probably it's 4. 4 times 6 is 24. The remainder is 2. What does this mean? It means that if I take 334 periods, so the last term of the last period is 2/3. In other words, I can subtract the remainder. I know 2004 is divisible by 6. So we usually use 3 dots to represent the fact that something is divisible by something. So 2004 is divisible by 6 with no remainder. So the term numbered 2004, I mean the order number of which is 2004, is divisible by 6. That is, it's 2/3. And again, we are interested in 2006 term. That is, I have to go by foot. I have to go 2 units like to the right. This is 2006 term, which is 3. Where's 3? It's E. Answer choice E. So I want you to pay attention to the fact that the 3 problems we just considered, they're slightly different. This is the sequence of numbers with a formula that expresses the next term in terms of the previous terms. In this problem, we had to construct the new terms using the word description, the sum of the cubes of the digits, and so on. This was pretty different. It was about the last digit of big power of 3. But in all these problems, what we saw, what struck our eyes first is big powers, big order number of the term they ask us. So in each problem, I had a belief in patterns. That's it. So your strategy is pretty easy. You write down the first terms, you catch the pattern, and you distribute this pattern to the numbers far away. That's it. I hope you liked this video. Feel free to ask any questions in comments section, and bye bye. See you.